Let's do this problem. 4.9. Determine the maximum tensile and compressive stresses in portion BC of the beam. So how are we going to do that? Well, first thing, let's find the reaction forces. And due to symmetry, we know that the reaction forces here are going to kind of be half of the total forces going down. So 15 plus 15 is going to be 30. So we're going to have 15 kips here and 15 kips here. Now that is useful. The maximum tensile and compressive stresses in portion BC of the beam. So we're going to need a couple things for that. For example, we can say that from inspection, we know that it's going to be right here. But if you're not sure, I would actually draw it out. So here we have one, and here we have another. We're going to do a shear and bending moment diagram, although it's not required by the problem. And so we're going to make some cuts. We're going to cut right here and right here and right there. So we're going to make these cuts. Let's see, we're going to have that one, and I want to do it in white. We're going to have that one right there. Then we're going to have another one here. I should give myself probably a little bit more space. So another one here. And then finally, we want to have one final one right here. So what we want to do here is we want to say we have our shear V1, our M1. Here we have our shear V2 and our M2. Here we have our shear V3 and our M3. And then here we're going to have our 15 in all of these. And what else? Well, here we're going to have our 15 going down, and that's going to be right here as well. And here we're going to have our 15 going down. So now that we have these things, we can say this is an X value. Again, this is an X value. And so now we can say that this is valid from 0 to 40 inches. And our V1 equation would really be 15. And that's pretty much it. And then what about our moment equation? Well, it would be 15 times X. So we can now evaluate them. And so we have V at A is going to be equal to 15. V at B is going to be equal to 15. M at A is going to be 0. M at B is going to be equal to 15 times 40, for which I need to get my calculator out. So give me a second. 15 times 40. I did not need my calculator for that. 600. All right, 600 kilopounds per inch. Kips, inches, and these are kips. Right? So this is going to be useful for us to plot it in a second. But now we want to do something else. Now we want to look at the second case, the second cut. So the second cut is going to be from 40 all the way to 40 plus 60, which is 100 inches. So what is going to be my V2? Well, I'm still going to have my 15, but then I'm also going to have a minus 15. And so that's 0. But and we were expecting that because we're talking about pure bending in the middle here, right? But this confirms it. And now M2 is going to be what? Well, M2, we're going to have a moment, and that moment is going to be 15x. Nope. 15x minus 40, right? Because we don't want to take that. But that's for the second. Hold on. My first 15 is going to be 15x, and then that's going to be a negative moment because it points downward. Well, that's not the convention. The convention is that if it makes it smile, it's going to be a positive moment. Makes it frown is going to be a negative moment, x minus 40. And that's it. So now we can actually simplify this. 15x minus 15x plus 600. And we see that the moment is constant, which makes sense because it's impure bending. So V2 is going to be 0, not V2, VB. Because this is VB from the left, this is VB from the right, and then VC from the left is going to be 0. MB is going to be 600. MC is going to be 600. All right, so now we do one more where X starts at 100 inches and ends at 140 inches. And so now we're going to look at that third cut. We're going to see V3 is going to be equal to 15 minus another 15, which is negative 15. And then our M3 is going to be 600, whatever we had before. But now we need to add minus 15 times x minus how much? Well, how far is the second 15? It's 100 away from the start. And so we get 600 minus 15x plus 1500, which is going to be 2100 minus 15x. And so now we put 100, and if we put 100, what do we get? Hold on. For V, C to the right is going to be minus 15, and VD, I believe, D left is going to be minus 15 again, because it's a constant. But for MC, we should get 600. Well, let's see. If I put 100 and I do 2,100 minus 1,500, it's 600. And then MD, we should get 0. If I put 140, so 140 times 15, that's 2,100, so you do get 0. So that's how to calculate all your equations. Now we're going to extend this and plot it so that you will visually see what we're trying to do in this problem. So here we want to take this and say this is my x-axis here. And so we'll do a couple things. We'll say this is my V in kips, and we'll say this is my M in kips inches. Okay? So we look at the first one, and we see V1 is 15. So we go from here to 15 right here. And we're going to write 15. Then what happens? Then we're constant at 15, and we get to B. We're still at 15. We're still at 15. But then we go to 0. And we stay at 0. That's what it means to be in pure bending. And then we go down 15. Stay here. And then we go back to 0. So this is also 15. Okay? So that's our shear. And then we do our moments. The moments, so here, if it's a line, we're going to have, if it's a horizontal line, we're going to have a line with a slope. We're going to get from 0 to 600. So bang, right here. Then it's going to be constant. And then bang, right there. And this is 600. So that's how you would do that. And then you take, since you know your flexure formula is sigma x is equal to minus mzy over iz. We know we have to find the moment of inertia about the z-axis. Now, the x-axis is coming out like this. This is my x-axis. My y-axis is going up. So you use the right-hand rule, and this is your z-axis. So we have to find the moment of inertia about that. So how are we going to do that? Let's do that right here. So for the moment of inertia, we can break this into two parts. We can say this is 1 and this is 2. And we'll say that I1 is going to be equal to its area, which is 2 times the base, which is 9. 2 times 9. Hold on, actually, that's going to be later on. So the first thing we want to do, it's a rectangle, so it's going to be, the base is 9, the height is 2, and then we're going to want to shift it to get to the centroid of this whole thing. But yet we don't have the centroid of that whole thing. So that's the first thing we actually want to find. So how are we going to do it? Well, we're going to do the area of the first, which is 2 times 9, times wherever its centroid is, which is at 1, halfway through its height. And then we're going to do the second area, which is 6 times 3, times wherever its centroid is, which is at 3 and another 2, so at 5. And then we're going to add the two areas together. So what is this going to be? Well, this is going to be 18 plus 18 times 5 divided by 2 times 18. So we can simplify kind of. We can say this is 1, this is 1, this is 2. And so what do we get? We get 6 divided by 2, which is equal to 3. Now, does that make sense? 2, 3, we're saying the centroid is right here. I think I could go with that. And so, hold on, I want to make sure in my notes that I'm not misleading any one of us and that I'm getting the correct answer. Let's see right here. I don't think I did it. I did this problem in my notes. Okay. I actually found it. It's 3 inches. Good. So now that we have this, we can go ahead and find the moment of inertia of each of the two parts, and then we put them together. So for shifting it, we're going to use the parallel axis theorem. So that's still going to be the area times the distance from the neutral axis. Now, if this is at 1 and we want to get to 3, the distance is 2. And so we need to do that. Now, I2 is going to have 112 times the base, height, the area, and shift it by what amount? Well, we know this is going to be at 3 here. So its neutral axis is going to be here. We want to get to this, which is at 3. And we're starting from 2 plus 3, which is starting from 5, so we need to go 2. So again, that is 2. This is where you might make mistakes. And so that's 1 over 12 multiplied by 9 times 2 to the third, plus 18 times 4, which is 78. 78 inches to the fourth. And then the other one is going to be 1 over 12 times 3 times 6 to the third, plus 3 times 6 times 2 squared, which is 4. So that would be 198. And that's where I make my mistake. That's where I make my mistake. So let's see. 3 and 2 is going to be 5. We want to get to 3. So that would give me a 2 here. Our area is 6 times 3. And 6 is to the third. And I see what happened. I need a times here. And we get a total of 126 inches to the fourth. So the I is going to be I1 plus I2 now that they are from the same neutral axis. And so it's going to be 126 plus 78, which is 204 inches to the fourth. So now that we have our I, we can calculate the max normal stress, tension, and in compression. So for sigma in tension is going to be minus m. Well, the highest is 600, and y is going to be, is this a symmetric cross section? No. So let's do, this is going to be compression, so we'll go to the top. And so how far are we from the top if this is 3? Well, we need to get to 2 plus 6, which is 8. So we need 5 more, so we're 5 away from the top. And then we're going to divide by 204. And then for tension, we're going to go to the bottom, which is 3 away. So we get 600 times 5, all of that divided by 204, and that's going to be 14.71. And remember the units, so we have KSI, because this is kips times inches. This is inches, and this is inches to the fourth, so we get kips over inches squared, which is KSI. And remember that it's negative, so you'll indicate compression. And then the other one is 600 times 3 divided by 204, which is equal to 8.82 in tension because it's positive. So you have tension and compression, and this is the answer. So you didn't need to do the shear and bending moment diagram, as long as you could recognize that here is going to be where your highest moment is. And you should be able to sketch this even without using the formulas, but this was a good review. I hope this was useful, and I'll see you next time.